Hello and welcome to Deep Dive Physics. Today we will talk about dispersion of light, angular dispersion, dispersive power of the prism, deviation without dispersion and dispersion without deviation and their formulas. We know that every ray of light with different color has different wavelength, and the red one on this side has a higher wavelength and violet and blue on this side has lower wavelength. Now we also know that the refractive index is defined as velocity of light in vacuum divided by velocity of light in the medium. If you watch our video on variable refractive index, you may also know that the refractive index actually varies with the wavelength of the light, right? So for example, velocity of light in vacuum here is c, and the velocity of light in a medium we can write lambda in that medium into frequency, right? So now refractive index sort of behaves like this, which means that for lower value of wavelength we have a higher value of refractive index, and for a higher value of wavelength we have a lower value of refractive index. So with this formula basically we can write for red light having higher wavelength we expect the refractive index to be lower. So refractive index for a red is going to be lower, and when we have a lower wavelength for blue, the refractive index for the blue is going to be higher than the red, right? Now when we look at the refraction, right, we know that if we have a higher refractive index, basically that ray is going to bend more. So suppose a ray of light is coming from air to the glass, and here the refractive index for the blue is REB or RB, and refractive index for the red is RR, right? So blue light is going to bend more, right? Similarly, when it is going from the dark denser medium to a lighter medium, again it is going to bend more because the blue has a higher refractive index. It is going to bend more, and red is going to bend less. Similarly, if we pass the light through the prism, right, so we have a slit here and we have a red glass put in here so that only red light is passing. We expect the ray of light to go like this and then bend, right? So this is the bend or deviation which we discuss in the prism. So deviation for the red light, and for the blue light it is going to be bigger, right? So deviation for the blue light is going to be bigger than the red light. Now if we pass sort of a white light which composed of all these wavelength, basically you will see, and you may have experienced it, that you will see is what we call a sort of spectrum, right? Now this side what we cannot see here is infrared, and here ultraviolet. There are more spectrum, but our eyes are not able to see them, so we see the spectrum. The red light, as you can see, is bending less, whereas the blue light is bending more, right? So this is the deviation for the blue, and this is the deviation for the red. Now this phenomena of sort of dispersing the light, right? So the light is coming and the sort of getting dispersed over here by the prism is called dispersion. So let's define that. The phenomena of separation of colors by the prism is called dispersion, right? Sort of disperse the light in different colors, and we are able to see those colors. Now in here you want to know how much is the dispersion, right? So here you can see that the red light is sort of getting turned by a smaller angle, right? So let's call it theta r, and blue light is getting turned by a bigger angle called theta b, and difference between that, so this angle is the basically what we call angular dispersion. Let's call this angle theta. Difference between the blue and the red is called theta, and it is the angle between the red and the blue rays. Okay. Now we can simply define this theta in function of the deviation. We have already noted that, right? So the ray of light for the red is sort of getting deviated by dr, right? And the blue light is getting deviated by db, right? So this theta is going to be equal to db minus dr, right? The difference between the deviation experienced by ray of light, the blue and the red one. Now show you a graph. So here it is, right? So we have this total deviation between the red and the blue. That's theta is the angle of deviation, or angle of dispersion, sorry, angle of dispersion, so on and so forth. Now if we sort of plot the lambda with the refractive index, right? So on this side we have the refractive index, this side is the wavelength. What we get is sort of a decreasing graph, right? So the refractive index depends upon the wavelength of the light and it is a decreasing function, and refractive index is inversely sort of proportional to the wavelength, right? So for higher wavelength, Re is greater, and for lower wavelength, so for a higher wavelength Re is smaller, for a lower wavelength Re is bigger, right? That is clearly evidence from this chart, right? So here we have a lower wavelength 400 nanometer, then you have roughly 1.85 and 1.82, and then sort of at 700 you have 1.74, something like that, right? So this is how it varies. Now there are different ways, using different formulas you can express that, and by experiment we found a couple of formulas. I'll just mention it for you. So one is n is equal to a plus b divided by lambda square, right? So we didn't say that it is directly proportional, we said it's a function here, right? So it's a function, whereas this one depends like a lambda square, and where a and b are constant and a is sort of given, a and b are constant for a given medium. And suppose we sort of differentiate it with respect to lambda, you will get Tn by T lambda into minus 2b divided by lambda to the power 3, and it is a decreasing function with a negative sign, and that sort of shows the slope of that curve we were interested in. Another way of sort of finding, people have found a different function like n varies as n is equal to n naught plus c by lambda minus lambda naught, whereas n naught is given to be 1.586 and lambda naught is 2.29 into 10 to the power minus 5, and c is 0.1 into 10 to the power 5. So if you get all these, basically just by plugging in lambda, you will be able to find the refractive index. And sometimes the question will be given like that, right? So you will need to find the refractive index as it varies with the with lambda. Now, as we said that, the prism sort of does two things, right? If you recall from our last video also, first we discussed prism does two things, right? First is it changes the direction of the light, right? So it is coming, sort of deviates, so it does deviation of light. And second, as we have experienced now, it's called dispersion of the light, right? So now you can watch the deviation formula we derived earlier, but I will just do it again for you, right? So let's say we have a prism here, the small angle. So it's a small angle prism, okay? So A is sort of a small angle, let's say less than 10 degrees. And then a ray of light is sort of inciding on this surface, and this I1 is also a small angle, okay? These are the assumptions we are making, right? So it is almost at the normal. So when it comes to n, basically it will get refracted, and let's say the refractive index for the ray of light here is n, right? It will get refracted and the R1, and then it will come here at R2, it will incident and then again go out, right? Now as we said, the A is small, because I is small angle, the R1 is also going to be a small angle, right? Because it will multiply by sine of R1 and it will be small angle. Similarly, the R2 is also going to be small angle, and for that reason I2 is also going to be a small angle, okay? You will get in a minute why we are assuming all that, right? So now let's write the Snell's law at the interface here, right, at M. So we'll say sine of I1 into 1, right, which is air, is going to be equal to n into sine of R1, right? And because these angles are small, we can simply assume it is an angle. So I1 is going to be equal to n R1, okay? Similarly, we'll write our Snell's law at point n for this interface, and it is going to be n sine R2 is going to be equal to 1 into sine I2, and because these angles are small, we can again say n R2 is going to be equal to I2. So now we have a value of I1 and I2, and now let's find out what is going to be sort of deviation, right? Now deviation here, it is coming at this angle, right, and then getting deviated. So what's this? If we sort of extend this, it's going like this. It was going at angle I1 and then got deviated, right? So the deviation on the first interface is going to be I1 minus R1, okay? Now here the ray of light was going like this, right? Now it got deviated like that, right? So the how much deviation addition is here is this is the I2 minus this angle R2, right? So it is going to be I2 minus R2, and this is going to be total deviation, and that is what we are interested in. Now we do know I1 and I2, right? And somehow we need to also find a relationship between R1 and R2 in terms of A, because A is only known, right? We do not know exactly R1 and R2, so we need to find that relationship, and that is very easy to see here. So this is A, right, in this triangle. This is A, and then the ray of light is coming like this, and if we draw a perpendicular from here, it's going to cut somewhere here, and this angle is also going to be A, right? This angle from here, R1, R2, and you will find that R1 plus R2 plus 180 degrees minus A is going to be 80, right? So this is R1, R2, and in this triangle, look at this. This is R1, right? This angle, this is R2, and this angle plus 180, right, is going minus A. So this is A, this is 180 minus A, right? So look at this triangle, say, only. This is R1, this is R2. Now this is A, right? So this is 180 minus A, right? So R1 plus R2 plus 180 minus A is equal to 180 in a triangle, and we'll get a relationship like that, which will say R1 plus R2 is going to be equal to A, right? You just take it on this side and we'll have that relationship. And now we are going to put that all these two equations here to find our deviation. Okay, so this is I1. So I1 is equal to nR1 minus R1 plus I2 is going to nR2 minus R2, and finally it is going to be n minus 1 into R1 plus R2, and n minus 1 when we here is A, and that is going to be our deviation. Okay, so for a small angle prism, generally you just need to remember this. This is a very important formula, so I'm going to write it down. For small angle prism at small angle of incidence, deviation by the prism is equal to deviation n minus 1, right? So if A is given in radian, the final deviation will be in radian. If A is given in degree, the deviation B is going to be in degree, and it is independent of the magnitude of a small angle of the incident of the prism, so we will not worry about that, right? So this is the deviation formula we'll be using, right? So now with this formula, right, as we said earlier, in case of dispersion, right, in case of dispersion, let's define few definitions here, right? So we said that dispersion is nothing but the angle of deviation, right? So we were interested in the angle of dispersion, which was basically the difference between the deviation produced by the blue minus deviation produced by the red, right? We have already defined that here. Okay, over here, like dB minus dr. So now we can exactly put in the formula and sort of start getting some results, right? So let's say the when the blue light is coming for the blue light, right? Let's say the refractive index is NB, and for the red light, the refractive index is NR. Okay, so what is going to be deviation for the blue light? It's going to be NB minus 1 into the same angle minus here NR minus 1 into A, right? When we do that, basically we'll have NB minus NR into A, and that is going to be equal to theta. That's what we are looking for, the angle of dispersion. Okay, so this formula is also important, right? So please remember that. Now we can simply do one quick example here. It will just clarify the concept. Okay, so now for this formula, right, let's say we have a prism of glass, let's say crown glass. Okay, there are different kind of glasses, crown, flint, etc., right? So where NB is given to be 1.521, and R for the red is 1.510, and A is, let's say, A. Can we find this theta? Yes, pretty easily. We can simply plug in the number. So it's 1.521 minus 1.510 multiplied by 8 degrees, and that is going to 0.09 degrees, right? That is going to be angle of dispersion. Now let's define a new thing, right? So we know this is the angle of dispersion, right? So now this theta, right? So let's define something called mean dispersion. Okay, so what is mean dispersion? Is going to be sort of when a ray of light comes, some dispersion happen. We know that here's the blue one and the red one get least. Yellow one is somewhere in the middle, right? So let's call that mean, right? So for the on the similar argument, let's say the mean dispersion is something basically the deviation of the yellow light, right? So the refractive index for the yellow is going to be the average of this NB plus NR by 2, and in this case when you plug in the number you will get 1.515. okay, now the mean dispersion or D mean is also going to be D of yellow is going to be n by minus 1 into A, right, like this, and this is going to be 1.515 minus 1 into 8 degrees, and that's going to be 4.1 degrees, right. Now let's define another quantity, what we call the dispersive power. Okay, so we are going to define another one called dispersive power, denoted by omega, which is nothing but the angular dispersion between blue and red light phase divided by the mean deviation. Okay, mean deviation of dispersion. So in here we have already have these numbers, and we can find that out, right? Now let's do an example so that we are more clear on this, right? So let's say given we have a crown glass prism X, and a flint glass prism Y. For blue light, for red light, and for the yellow light, or the mean one is here. The refractive indices are 1.521, 1.665, 1.510, 1.515, 1.645, 1.655. Now let's find out the angular dispersion for the X or a crown glass. What is it? Will be NB minus 1 into A minus NR minus 1 into A, and that is going to be NB minus NR into A. We already know NB and NR for the crown, so it is going to be 1.51, sorry, 1.521 minus 1.510, and let's say A is given to be 8 degrees, so multiply by 8 degrees, and this is going to be 0.09. Now we can find the mean deviation. And that is going to be this one, ny minus 1 into 8 degrees, right? So that will be equal to 1.515 minus 1 into 8 degrees, and that is going to be 4.1. And now we can find the dispersive power by taking the ratios of these two, right? So the dispersive power omega is going to be equal to 0.09 divided by 4.1, and which is going to be 0.021, right? If you do that, the same calculation for the flint glass Y, you will reach at the number. So for the dispersive power for the X and for Y, you will reach at 0.16 divided by 5.24, and which is going to be equal to 0.03, right? And as you can see, the dispersive power of the flint glass is roughly 1.5 times, right? So these numbers, they are looking small, right? But they have quite an effect on the dispersive power, right? So dispersive power you can simply calculate using this formula, right? Now let's try and derive a general formula for dispersive power. Okay, so here as we said, the dispersive power omega is going to be equal to dB minus dr, deviation of the blue and red, divided by the mean deviation, right? So what is dB? dB is nothing but NB minus 1 into A, right? And dr is NR minus 1 into A, and D is equal to N for the yellow or average, or A, right? Let's put that in here, and we have NB minus 1 into A minus NR minus 1 into A divided by N minus 1 into A, and the A will cut off, and then whatever remains is basically NB minus nr divided by n minus 1. Okay, so this dispersive power omega, we have a formula now, which is nb minus nr divided by n minus 1, and now we can simply see that it depends only on the refractive indices, doesn't depend upon A. Okay, so this dispersive power of a prism only independent of A. Now we'll also note that this dispersive power is a ratio, right? So it has no units. So it's a ratio and has no units. Whereas the angle of dispersion, right? The dispersion angle theta is given by nb minus nra, and that is an angle, right? So it could be in angle or sorry, radian or degrees, right? Now let's look at what we call, can we have something where we can have some deviation but without dispersion, right? As you said, the prism does two things, right? It does deviation and dispersion, right? Can we make some equipment where we have deviation without dispersion? Okay, so imagine we have a prism here which is made of a crown glass, right? So ray of light is coming like this, it is going to deviate it like this, right? And then we have another filled glass, different kind of a prism, which is like this, and it is in opposite direction, so ray of light will deviate. But because the dispersion is happening in a different direction, the ray of light is actually coming parallel, right? And because it is coming parallel, the dispersion is eliminated. Okay, so you will not be able to sort of distinguish between this red light and other frequencies, because it will be very very thin, and sort of there will be no dispersion, right? So because these are parallel, dispersion is eliminated, right? So let's calculate that and see what happens, right? So what should be the case for that, right? So let's say this is a prism A, right? So the dispersion by prism A is going to be equal to NB minus NR into A, right? And this is going to be in the downward direction, right? But for the prism B, it is going to be, let's say, NB dash NR. So these are the refractive index of blue and red light in the Q prism, right? And let's say this angle is A dash, right? So we can have an arrangement, and it is going to be upward, right? Now we can have this arrangement, the prism made of different glasses and different angles, so that we can have this, right? So let's find out that condition, right? So if there is no dispersion, basically for no dispersion, we can write, for no dispersion, this has to cancel out, right? So one is downward and one is upward, so this has to be equal, right? So we'll say NB minus NR A should be equal to NB dash minus NR dash into A dash, right? So let's take an example, right? So let's say we already have that data which we have written here for the clown and film class, and we're just going to plug that in, right? So forgot, here is the data, right? So here's the table, right? So we are going to plug these numbers in and find out at what value of A dash basically, you know, we can achieve this, right? So NB is here, which is 1.521, right? And R for the crown is 1.510, and for the flint NB dash is 1.665, and for the red 1.645, and then A, let's say 6 degrees, right? And let's find out what will be the angle of second prism. That's going to be NB minus NR divided by N dash B minus N dash R, right, into A, and when you plug in the number, you'll get 1.011 divided by 0.02 into 6 degrees, and it will turn out to be 3.3 degrees, right? So if we can have a small angle prism with A 3.3 made of plane glass, right, and if you pass a light like that, basically we'll only have deviation but no dispersion, right? So that is a satisfying criteria. Now let's find out how much the basically the net deviation is going to be, right? Because we haven't found that out yet. So now how much is the deviation? So for the prism A, okay, the deviation is going to be, for the first prism is going to be n minus 1 into A, and for the second prism, and this deviation is downward, right? Now this other prism is upside down, right? So this time when the ray of light is coming, the deviation is going to be upward, right? And this time it is going to be n dash 1 into A dash, and this is going to be upward. So the net the deviation is going to be n minus 1A, and minus, because it is now upward, n dash 1 minus A dash, and when you plug in the numbers, we already found A dash to be 3.3, and we already have these numbers in the last table which we have given. We'll get the net deviation, right? Deviation is going to be equal to 1.515 minus 1 to 6 degrees minus 1.655 minus 1, and here to 3.3 degrees, and finally it is going to be 0.93 degrees. Okay, so this kind of problems usually comes in the exam, where you have to be very clear about if the dispersion is happening or if, without deviation and things like that, right? So now let's look at the other case where we try and do sort of what we call dispersion without any deviation. Okay, so second case, which is dispersion without deviation. Okay, so now we know the formula, right? So in this setup, basically you have a crown glass prism and the flint glass prism. They are placed like this, right? And again the same thing, we have this angle A known and A dash we will determine, right? So let's first find out, we want no deviation, right? So let's write down that condition for this to happen, right? So for the deviation of the first prism, it's going to be n minus 1 into A, right? And if the prism is like this, it is going to be upward, right, in the upward direction. And deviation from the second prism is going to be n dash minus 1 into A dash, because prism like this is going to be in the downward direction, right? So prism is like this, the ray of light is coming, so it deviates like this, right? And so it is downward for this one, and this for the upward for this one, no doubt. So net deviation, we want it to be 0. Hence this 2 has to be equal, so n minus 1 into A has to be equal to n minus 1 A dash, right? Now let's find out the value of A dash for this condition. What should be the A dash? A dash is going to be n minus 1 A divided by n dash minus 1, and when you put in the number, that's going to be 0.515 0.655 into 6 degrees. Given for the A, you will arrive at 4.7 degrees, right? So slightly bigger angle prism compared to our last case where we had 3.3. So we have like 4.7 prism. Basically, you know, we can sort of have no deviation and only dispersion. Okay, so now let's find out how much the net dispersion is going to be, right? Like we found out how much was the net deviation in the last case. So net dispersion, right, is going to be, again for the blue light, NB minus NR into A. This is for the first prism, right? And for the second one, in negative direction, NB minus NR dash going to be A dash, and when you plug in this number, now we know the A dash as well, 4.3 4.3 4.7 degrees, and we have all these numbers in here, and we plug that in. Basically we get 1.521 minus 1.510 to 6 degrees minus 665 minus 645 to 4.7 degrees, minus 0.028, which means negative sign, which means in the upward direction. Okay, so in the exams basically you will get and should be able to calculate all these things, right? So what we learned today are very simple things. We learned that why the dispersion happens, right? We derived a formula for the angle of dispersion, which was basically the difference between the deviation of the blue minus deviation of the red light, right? Then we derived a formula for the omega or dispersive power, where we said it is nothing but it is equal to the angular deviation, right? Angular dispersion divided by the mean deviation, right? And finally we derived a general formula for omega, which is equal to NB minus NR by N minus 1, and we noted that it is independent of angle of the prism, and also it is just a ratio, and it has no unit because it is a ratio, right? So with that, basically we'll close today, and we also derived the formula for dispersion, right? So dispersion was here, the angle of dispersion, it turned out to be, when we do that, theta is equal to NB minus NR into the angle of the prism. Okay? So with that, basically we'll close and work out few problems in the next session. This is a important topic, and every time I have seen the questions coming in the exam for these two cases. So next video we'll try and sort of do few problems from this session. Till then, if you want and watch more videos, you can go to deepdivephysics.com and also subscribe to our channel. We provide one-to-one and small batches tuition for IIT JEE mains and advanced. If you are interested, please get in touch. We'll provide more details.